So now we're going to get out of the data display and look at data analysis methods. So we're going to cover all of these data analysis methods. The first one is what we call the measure of central tendency. There are several different ways to measure the center of a data set or the middle of a data set and how it's spread apart. The mean and the median are two measures of central tendency that try and tell us where the center or the middle of the data is. The range, interquartile range, and other values tell us how spread out the data is in reference to the other data points. The number that's commonly used to characterize the middle is called the arithmetic mean. That's an average. So just like you would find your average grade in a course, you're adding up all the values and dividing by how many values you have. That's going to be the mean. We call this the arithmetic mean, but you're basically summing up the values and then dividing by how many you have. So if I'm looking at the mean as a balance point, the idea being that there's an equal distance from the possible data set values to the mean. Now, that doesn't mean to say there might be a mean where there might not quite be a value there, just like we're seeing here, and that's okay. So we're still finding it by adding up those data points on the line graph, and then we're dividing to be able to find out what the actual mean is. But notice there's no actual data point there in the 5 because it's not the middle data value, it's the middle of the spread of the data. It's possible to then rearrange the data to have the same mean, but be spread very differently. So if I could start looking at choosing different values, that's going to adjust the mean and look at just what the mean actually is. So if I start changing the values of the data set, I can change the value of the mean. I can also look at displaying the data slightly differently, and outliers can affect the mean as well. To compute the median, that is the literal middle number of the data set. So you're going to arrange the numbers in order from least to greatest. If it is odd, the median number is in the middle, easy peasy. If it is even, you're going to find the mean of the two middle numbers by adding them together and dividing by 2. The median is usually reported with something called an interquartile range, which is a measure of spread that gives the middle 50% of those scores that lie in the median in that range. The mode is a less used measure of central tendency, and it's just something that occurs the most times. The mode is going to be what occurs the most, but that's exactly why it has a weakness as a measure of central tendency. We typically use a mode with categorical data because it's very difficult to add categories together. It's impossible to add them together and divide. So the mode is really just reserved for when we don't have numbers. Here's some examples of finding the mean, the median, and the mode. To find the mean, I'm going to add my data values. There are 6 of them, so I'm going to divide by 6, and there's my mean. For the median, I have them already arranged from least to greatest. There's an even number of data values, so I add the middle 2 values and divide by 2. This set is bimodal because 60 and 95 occur the exact same number of times, so that means I have to share the mode between them. Choosing the most appropriate way, typically the mean is going to be the most appropriate unless it's a categorical value. To look at this example, we have a company that employs 20 people, so sample 20 people. It gives me the earnings of the different people. Is the mean the best number to represent that salary? So let me find the mean. Well, once I find the mean, I'm kind of like, I don't know. In this case, the mean is not very representative, right? Either the median or the mode, which would both be 10,000, would better describe what's happening here. And this is because the mean is affected by extreme values. That 200,000 is really pulling that mean a lot higher than the actual middle value. If 18 people made 10,000, the middle of my data set should be around 10,000. Let's look at this data set. Is the median the best representation? If I look at this, the median of it is 92, but I have a really wide range of values from 30 to 99. If I'm looking at 92, it's kind of clustered from that 92 to 99. So that's something to consider. It's probably not the best representation because I have a whole cluster of data drastically far down from 92. And so if I inferred 92, I'm going to assume, hey, everybody did great on this test, but 5 people really didn't. So in this case, the mean might be more appropriate because I can really see those lower values come through. Looking at this one, is the mode going to be appropriate? Well, first of all, the mode is 98. Does 98 represent the whole data set? No, it doesn't. I would probably want to use the mean or the median here. Looking at this data set, the median is going to put you at somewhere around 61-ish, 62.5. So it could make a case for either the mean or the median here. So let's consider this data set. The range, now we're moving on from measures of central tendency to measures of spread. The range is your highest value minus your lowest value. That tells us the spread of the data. The median, still finding from the middle number. Once I divide the median in half, it divides my data set in half at the median. And then I have what we call Q1 and Q3. Q1 can be found from finding the median of the first half of data. Q3 can be found by finding the median of the second half of the data. My interquartile range is found from doing that process and subtracting Q3 from Q1. So to find IQR, you first have to list your data in order from least to greatest. You then have to find the median of the whole data set. Where that median is, draws a firm line and divides your data set into 2 halves. You find the median of the first half, the median of the second half, and then you subtract the median of the second half from the first half. So when the interquartile range is reported along with the median, it just gives us a better picture of the spread of the data. Box plots are a more advanced way to show data, and they use the quartile range. When I'm drawing a box plot, I put a vertical line at the minimum data value and a vertical line at the maximum data value. Then I'm going to put vertical lines at Q1, Q2, which is the median, and Q3, and I'm going to connect those in a box and add whiskers to the side to the min and the max. Here is an example. If I'm looking at this data set, what are the minimum and maximum values, the median, and the upper and lower quartile range? Well, the minimum is 0. The maximum is 70. The median is 20, that middle bar. The lower quartile is 10 from the bar further to the left, and the upper quartile is 35. Now, using this whisker plot is very handy because an outlier is a value that is widely separated from the rest of the group of the data. In the data set that's given here, the data is very clustered together and there are no real outliers to be found. But if I alter this just a little bit, I have 21 and 150 that are potential outliers. An outlier is going to be any value that's more than 1.5 times that interquartile range, or Q3 minus Q1. Outliers are commonly shown with an asterisk. Whiskers are then drawn to the extreme points that are not outliers. So if I'm looking at this example, I'm going to first find the median, list it all in order from least to greatest, find the median, divide it into 2 different data sets, find the median of those, and then I'm going to subtract Q3 from Q1. My minimum and maximum value are 11 and 110, so I'm going to find my IQR. So my outliers are any score that is greater than 1.5 times my IQR, or less than, I'm going to have the subtraction of 1.5 times my IQR. 110 and 100 both satisfy those values, so they're both going to be considered outliers. So you see, an outlier exists beyond the whiskers almost. If I'm comparing sets of data, box plots are used a lot of times to compare. A stem and leaf plot is usually a cleaner display for one distribution. And parallel box plots, meaning 2 side by side, can be used using the same number line to help us represent them. The disadvantage being we can't really spot clusters or gaps in box plots because we're just getting those vertical line looks, and we can kind of see cluster values in a stem and a leaf plot. With box plots, we don't need to have sets of data that are about the same size like we do for stem and leaf plots when they're compared side by side. When I'm comparing data from two or more sets using their box plots, first you want to study those boxes to see where they're located in reference to one another. Then you're going to consider how wide or how long those boxes are. You're also going to check that Q1, Q2, and Q3 and compare those to one another as well as the whiskers. So when I look at these two parallel box plots, I can see that the male compared to the female has a much longer box, right? And it has a higher Q1 than a Q2 in female. Now we're going to move on to variations. We've had measures of center, measures of spread, and now we're going to look at variation. Variation is going to be an advanced idea to teach to your elementary students. So we're talking upper elementary here. So this is the measure of spread that's needed when data is summarized with one value, such as the mean or the median. It has to be numeric data. The simplest way to describe the spread of the data is the range, always is. I can also use the IQR to get a little bit more specific. The most sophisticated is what we call the standard deviation. This would be your upper elementary classes you would be showing this to. The mean absolute deviation makes use of an absolute value to find the distance from each data point from the mean. Then I take the mean of those distances, this is a very complex process, to give an average distance from the mean for all of the points together. Then I'm going to compute the mean absolute deviation of a certain number of values. So I'm going to take the measure of the distance, find the absolute value of each difference, add them up, and find the mean. That's a lot of steps, guys. So when I do this, this is basically what it's going to look like. I'm going to take my data value x1 and subtract the mean that I found. Take the absolute value of that. Plus data point 2, subtract the mean absolute value. And I'm going to do that until I run out. So here is a data set. I found the mean, which is going to be 83.2. And then I did 99 minus the mean, 67 minus the mean. So you see this? And then I took the sum of those means right here and divided by the number of data points. Now, once I look at the pictures of this, I'm going to see that I'm given a set of test scores that are shown in these figures. And if I mark the mean here in the bar graph and I draw it across the mean of 82, that's going to give me a little bit better of a visual of what's happening here with the mean. The variance and the standard deviation are going to build upon that mean average score. So if I want to compute the variance, I'm going to follow a very similar process. I'm going to find the mean, subtract the mean from each value, and then I'm going to square it. So instead of the absolute value, I'm going to square it. Then I'm going to add them up and divide by the number of values that I have. So it's very similar to the mean. Then I'm going to take the square root of that, which is going to be the standard deviation. So this is what it looks like. Instead of taking the absolute values of those subtraction statements, I'm squaring them. And then I'm going to divide by the number of data values and take the square root. So here is an example. I'm going to use this data set to find the following items. So in exam A, I find the mean by adding up all my values and dividing by the number of values I have, which is going to be 3, 4, 5, 6. Do the same in exam B. The range is the highest score minus the lower score. And then if I did the complete calculation, I'm going to find the mean. I'm going to say 0 minus 50 plus 0 minus 50 plus 0 minus 50 plus 100 minus 50, 100 minus 50, 100 minus 50, all divided by 6. And then that's going to give me the mean of my absolute deviation. And remember to always use those absolute values. If I wanted to find the standard deviation, I'm going to follow that similar process, except this time I'm going to square those differences. So in this, instead of showing 0 minus 50 3 times, I just did it 3 times 0 minus 50, instead of saying 0 minus 50 squared plus 0 minus 50 squared plus 0 minus 50 squared. To find the median, I list them all in order and find the middle number. Inner quartile range, I'm going to find Q3 and subtract Q1. Now, the graphs of normal distributions are bell-shaped curves. Um, a bell-shaped curve for a student is very difficult to visualize. It's a hill. We want to see a nice, even hill that slopes down the same one way to the other, and that's going to be called a normal curve. When we have a normal curve, the mean, the median, and the mode are all equal. They're all the exact same number. It doesn't happen very often. And it goes indefinitely onto both sides, and it's very symmetrical. So if we look at this, this is kind of that nice hill. It's going to slope down the same on both sides. And if I folded my paper exactly in half, I would have a mirror image. In a normal curve, about 68% of the values, so 34 plus 34, occur in the first standard deviation. 95 occur in the first two standard deviations, and so on. I suggest printing out that previous slide. The percentages represent approximations of what percentage of the data lies between those two values. So let's look at an example. I'm giving a standardized test. If it's a standardized test, it should follow the bell curve. And I want to see how many people scored between a 400 and a 600. I'm going to find the standard deviation of 100, and I have a mean of 500. So 500 is going to be this middle value. Let me go back to my screen. This is going to be 500, which means this is 600 and 400. So 68% of the values fall between 400 and 600. And that's where that value is coming from, because I'm taking the mean and adding the standard deviation to get the right side, subtracting it to get the left. And I'm going to follow that same process to get the other two. If I want to apply things to the normal curve, I can say, well, if I wanted to curve my tests, I could force a normal distribution to happen. So what I can do is sort of fit my data to a normal curve by making adjustments in those test scores. So here, if I'm looking at based on the normal curve, the table shows the range of grades the teacher might assign if the grades were rounded. A percentile happens when I'm taking a standardized test and they report, right? You're in the 10th percentile, you're in the 20th percentile. We hear a lot about that. The percentile puts your score in terms of other scores on the test. So it's irrelevant to everybody's performance. Percentiles divide the data into 100 equal percents. Deciles are points that divide a distribution into 10, so versus one at a time to 10 percentage deviations. The rth percentile is represented as P sub r. What does this actually look like in a problem? Well, here's my sample problem. I know the median, they gave me that, so I know 50% of the distribution has to be less than 500 if it's normal, and 50% has to be greater than that. Since 600 is going to be one standard deviation above the median, 84% of the distribution is less than 600. Where is that coming from? Well, if the middle is 500 and this is 600, I'm going to have 34 plus 34 plus 13.5 plus 2.5. All of those scores lie below the 600. So that's where that percentage is coming from. Here's another example. If Ozzy is ranked 25th in the class of 250, what is his percentile rank? Well, I'm going to take 250 minus the 25 because he's ranked 25th, which puts him as 225 in the numbering system. So that means that 225 ranked below him and then 25 ranked above him. So if I did 225 divided by 250, that's going to be 90%. So 90% of the class ranked below him. So that means that he ranked at the 90th percentile. Here's another example. And since Kathy's percentile rank is 60%, that means 60% of the class ranks below her. So therefore, Kathy is 20th in her class. So this time we're working backwards from having that percent.